Okay, so let me start. I hope I'm audible. Am I, Aditya? Okay, perfect. So, good evening. This is Abhimanyu, and welcome to this sixth week of interactive session. Uh, so, we will be first going through all the topics that professor has taught us during the week 6 of the recorded lectures. Then I will go through the non-graded assignment. We will try to solve that, and then I have some sample problems which I have not coded yet, so we will be coding them together. Fine. So we will be starting with the differentiation of single variable. Eventually, we will go to the multivariable or partial derivatives. Then we will look at the integration methods, numerical integration methods. Finally, we will be looking at two of the MATLAB functions, TRAPZ and CORD. So, okay, first let us look at. Mm, yeah, Aditya, do you have any doubt?
No, sir, you can start now.
Okay. Yeah. So the definition of differentiation is that we try to find we try to we try to find the limit of a function. Like we choose 2 points. We choose 2 points on the function which are separated by a very small distance h, and we evaluate the function at both of these 2 points, and then we divide by that distance. And as that distance h tends to 0, we get the differentiation of the function. This is the basic definition of the differentiation. We will be and this is also called the forward difference formula for the differentiation. And also, if we look at the Taylor series approximation of fx plus h, then the expansion like up to three terms, the expansion can be written like this. And then if we neglect the last term, then we get this formula for the derivative of f of x, and the order of this, like the higher order terms which we neglect, we get these in the order of the equation. Okay. Uh, yeah, so we have three formulas for them. Uh, the forward difference formula, the central difference formula, and the backward difference formula. So the forward difference formula is similar to the what we get from this definition of differentiation. So fx plus h minus fx divided by h. So the smaller this h is, the much more the closer our function, and the closer is this function to the true derivative. Then there is central difference formula. So in the forward difference, we take 1 point which is to the, like if I draw number line. So if this is my point x, so in forward difference, I take a point x plus h, which is at a distance h in front of the function. In Yeah, so I divided by h. Whereas in central difference, I take 2 points, one at a distance h, which at front of this point x, and at a distance h to the rear of this point h, this point x. So I take these two function values at these 2 points, fx plus h and fx minus h, and since the distance between these 2 points is now 2h, so I divided by 2h. So this is my central difference formula. So the order of approximation of this is h square. So it's much more accurate as compared to forward difference. Then we have backward difference formula. Uh, so in backward difference, instead of taking the front point, we take the function value at the given point x, and at a point which is uh, before the point x, or to the back of the point x. So we take a point fx minus h divided by h. So this is the backward difference. So and the order of approximation is similar to the forward difference. like it's a linear approximation. So and but it is less than the order of approximation for central difference. So forward difference and backward difference are much more accurate much less accurate as compared to central difference. Right? Uh, okay, so I think this needs to be up. Fine. So this is clear. Let us look at an example. We will solve the same example which professor has taught us in the recorded lectures. Okay. Yeah. So instead of making a different function, I usually prefer the function handle because we don't need to create another function file. I can simply type it in here only. So I will be using this function handle only, but you can also create another file with the same function and we can call that file wherever we are calling this function handle. This is our function handle, a10x. I am evaluating the function at x is equal to 1 and I am taking the value of h as 0.001. So this is the forward difference formula. I'm evaluating at a point x plus h and at the point x, and then I'm divided by h. In the backward difference, I am taking the point to the rear of the x, and in central difference, I am taking 2 points, front and back of x. This is the exact derivative of tan inverse x, and I am evaluating my error. Yeah, and I'm evaluating my error as the absolute difference between the forward. Like this is for the forward only. This is for the backward, and this is for the central difference. Okay. So if I can. Okay, let me combine these two so we can see it. Value dash. This should be good enough. Central. Yeah. Exact derivative. Okay. So yeah, so this is the exact derivative, 0.5 at x is equal to 1. Using forward difference method, we get the value as 0.4998 and the error is of the order 2. Error is 0.002. For the backward difference, the error is 0.003, and in the central difference, the error is 0. If I do it like we want to see more number of digits, yeah, then we can see that it's like I am taking an h value of uh, 0.001, like 10 to the power minus 3. So my order of this approximation is 10 to the power minus, like it's in the range of 10 to the power minus 3 only. For this also, it's in the range of 10 to the power minus 3 only. And so these two are actually like order h. So I'm getting this value. My central difference is order h square. So I'm getting like 10 to the power minus 6, less than that, right? So we can see that the central difference is much more closer to the true value than the backward difference and forward difference methods, right? Uh, so any doubt in this? Simple. We'll go to the next part. Yeah, so that was like the first order derivative. Now if we go to the second or higher order derivatives, so we can simply write this like we can to get the second order derivatives, we can initialize with something like the forward difference or backward difference, and then replace these two with. Okay. So like I can take this is my central difference. Let's leave that and let us take the forward difference formula, and then I replace this of x this fx plus h uh, with another backward difference. So I will get like if I try to do a derivative at fx plus h, then I will get another, like I will get an fx plus h and an fx, and for this fx, if I try to use the backward difference, then also I will get this fx minus h minus fx minus h. So I will get two fx, and I will get a single fx plus h and single fx minus h. And since all of these will be divided by h, then that h goes to the denominator and it becomes h square, right? So that's how I get this formula for second order derivative. So you just need to instead of, you can get it using this also, but I usually prefer the forward difference or backward difference. It's much simpler. Just replace, you just use another, like if I'm using forward difference, I will use another backward difference for both of these, and I will get to the second order derivative. If I'm initiating with backward difference, then I will use forward difference for both of them, uh, and I will again reach this second order derivative formula. And the order of approximation is h square. And similarly, you can initialize with any of them and go to either use the forward derivative or uh, backward derivative, or even the central derivative, and you will get the third order derivative. Fine. The order of approximation for third order derivative is also h square. So each of these formulas are of the order h square accurate. So we'll look at the same example and we will try to find the second and third order derivatives. Yeah. So the same function handle, I'm evaluating at x is equal to 1 only. So let me use h as minus 3 itself. Yeah, so this is my first order derivative using central difference, my second order derivative, and this is my third order derivative. Uh, the same formula that I have mentioned before. So these all fx plus h, these are all, I am calling this function handle at different points. These are my exact derivatives. So the first order derivative 1 upon 1 plus x square, this is the differentiation of that, and then another differentiation of that. I'm calculating the error, absolute value of error, and then I'm just displaying them. So let me clear the variables. Okay. Yeah, so this we already saw, first order derivative using central difference. This is the second order derivative. So this is the value. Okay, the first one is the exact derivative. So this is the exact derivative. The second one is the value that we are getting using the formula. And third one is the error. Okay. So we can see the smaller the h, the smaller is the error. So if I make it 1e minus 1, so 0.1. Yeah. So now you can see the error has increased. Like if I use 0.1, So here my error becomes like order of h square. Here also it's a little bit greater than h square, like around thousand, like around yeah, it's also h square only. This is like h 10 0.1 10 to the power minus 4. Yeah, this one is 10 to the power minus 6, and this is like 10 to the power minus 2 only. Fine. And like the the smaller my h becomes, the smaller my error becomes. Okay. Yeah. So the more I reduce x, and the more I reduce h, the smaller my error becomes. Okay. Fine. Any doubt in this? And then, yeah. So okay. Okay, let us look at something else before that. Okay, so I am using the same a tan x function. We will try to find the same thing, differentiations backwards, like first order differentiation using forward, backward, and central difference methods for different values of h. Okay, and then we will plot a log plot of error versus h values. Okay, so we can see the optimum value of h, right? So if I run this, let me show you the code first. So this is the function handle. I'm defining again at x is equal to 1 only. This is my vector of h values. So this is 10 to the power minus 1 all the way to 10 to the power minus 10. Yeah, so like right now, this is since h is a vector. So I have done here element wise operations. So I have changed all these divisions to element wise. The rest of them are just function handle, and it's a simple a function, so I don't need to change anything else. Just need to make these divisions element wise. Okay. True value will remain the same, so no need to do change anything, and the error calculation and all the rest of the things are same. At the end, I'm just plotting a log plot for the error of for the forward difference method, backward difference method, and central difference method on the same plot. So red one is for the forward, green one is for the backward, and blue one is for the central. Fine. So I will just run this. Okay. Yeah, I think I changed the variable name, but let me just make this format short that it comes in one line. Mhm. So these are like column vector, column. Yeah, this is a row vector, right? So I'm just taking transpose to make them a column vector, so that comes like this column of these values, right? Backward. This should work now. Close, let's see, close. Okay, so yeah, so okay, let me plot h also side long side so we can see which value of h is for what. Um, sh- sh- okay, so the first one is for forward difference, different values of h. We can see that the error goes down as we decrease h more and more. But okay, let us see the graph. Fine. So so the red one is for forward, green one is for backward, and the blue one is for central. So we can see as I go on decreasing h and h further and further, uh, the best error that I get for central difference is for h is equal to 10 to the power minus 5. After that, the error again starts to increase because it's like order h square. So this is a log plot, and we can see if I take the ratio, like a ratio of these two values, then it should come out to be close to 2 because it's of order at h square, right? Whereas this is like a linear graph because it's order h. This is more of a linear graph for the forward and backward because it's of the order h. But I can see that I can decrease h to even further lower values like 10 to the power minus 8 until the error decreases, like up to 10 to the power minus 8 the error decreases, but after that the error again starts to increase. Whereas for the central difference, the best error that I can, or the minimum error that I can get is 10 to the power minus 5. After that, the error again starts to increase for the same function. Okay. So yeah, this is like why, because we are, the more we are decreasing h, the more we are doing the h is very small number, right? So we are dividing it. We are taking a division with h. So the overall this value becomes like uh, we are losing a lot of data. The more h we are reducing more and more and more, we are truncating part of the overall function, right? So that is why the error starts to increase after 10 to the power minus 5. Whereas for central and backward difference, the order is of like h only, so there is not much like nothing much happens until 10 to the power minus 8. After that, it again starts to increase, right? So this was for the truncation errors and round off errors. So yeah, we cannot go on decreasing h to smaller and smaller values. We need to find an optimal value and then use that value for the function. Okay. Let us try to yeah. So let us try to do the same thing for this example. So this is also a similar example, same example from the lectures. So I think I already have the code for this. Let me first close all. Um, I don't think I have the code. Yeah, I don't have the code, so I will just copy. We need to find the first and second order derivative, so I will just copy this. Yeah, so the good part is we just need to change this function handle, rest everything remains the same, right? So it's the function 2 minus x plus log of x. So a log of x is natural log. It's not base 10. If you want base 10, then you just need to write log base 10. Okay. Mm, yeah, so this is fine. I just need to change the exact derivatives. We are only doing the first and second order derivatives. So I will remove this third order derivative. And I will make this exact derivative. Okay. Minus 1 plus 1 upon x. And the second order derivative would become mm, mm, yeah, rest everything will remain the same. Okay. So we just need to change this function handle and the exact derivatives, because that we need to feed by the we feed it manually. Okay. I will save this. And we can check. Okay. Variable. Okay, sorry. So I need to remove this part. And now this should work. F prime 3 again. Kahan aa raha? Error 3. Okay. So we are not calculating the third order derivative. So just need to remove all those parts where the third order derivative is coming. Yeah. Okay. So the first one is the exact derivative. The second one is the calculated derivative, and the last one is the error. Okay. So in the first order derivative, 1, 2 minus x. Fine. Mm, yeah. So in the first order derivative, okay, so this is like 10 to the power minus 6. So it's a very small number. It's not 0.333. If I use a format long, then I run this. Yeah. So like these values are basically close to 0 only. So it's like 0.333 into 10 to the power minus 6. And this is also error is also 0.33 into 10 to the power minus 6. And for the second order derivative, this is the exact value and this is the numerically calculated value. So like after, yeah, so the error comes after the 7th decimal place. Okay. Uh, this is the benefit of this function handle method. We just need to change the function at one place and we can calculate the uh, rest of the program remains the same. So even if I want to do this derivative for some other function, I just need to change this function handle over here, the value at which I want to do the derivative, and rest I just need to put this exact derivatives manually by hand. Rest everything remains the same. Okay. So I will try to do this for multiple values of h and try to see uh, when our error starts to again increase. Okay. Uh, let me just write it like 10 to the power. So we start with -1, -1, and I will go till go to -5. I just need to do element wise over here and element wise operation over here. This will be a vector. This will be a vector. This will be a vector. Okay, fine. This should be fine. This should be fine. I will just add a h over here. Hope it does not give me any error. I will run it and see. Okay, yeah, so that should be element wise operation. Yeah, this is an h square. This is fine. Horizontal concatenation error. Error one. Okay, so this is h. What's the size of h? 1 cross 5. 1 cross 5. Everything is 1 cross 5 only. Why is the error coming? 1 cross 5. Yeah, so exact derivative is a singular value. Okay, so I'll just remove this. This is a scalar value, it's not a vector. That is why it's not able to concatenate. Should run. Yeah. So again, here the error is just yeah, for the second order derivative after a certain h, error again starts to increase. So if I make this like 10 to the power minus 8 and this again, similar to what we saw previously, we plot a log plot, h versus error 1. It's using green. Yeah, so similar to what we saw earlier, right? Okay, so green one is error 1 and uh, the red one is for the second order derivative. The first one is for the first order derivative. Yeah. So like even though both the functions are both the functions are of order h square only, the second order derivative starts to the error again starts to increase for a lower value of h then for the first order derivative. For first order derivative it goes up to like 10 to the power minus 5. For it starts to increase from 10 to the power minus 4 only. So this depends, like it will vary from function to function, but eventually the pattern remains the same. Uh, the error will start to increase early for the central difference formula, and then the error will start with decreasing value of h, and similarly the error will start to increase for smaller values of h for a second order derivative than for a first order derivative. Okay. the value of this h will differ from from function to function, but the pattern will remain the same. Okay, like we saw for the previously for a tan x, tan inverse x, this like we are still using the central difference. So for tan inverse x, it became yeah, this is the one, right? Let me plot this. Yeah, so it started to decrease from 10 to the power minus 5 only, and for the forward and backward, it started to increase after 10 to the power minus 8. Okay. I need to do the second order derivative also to check if it also starts to increase like after 10 to the power minus 4 or not. Yeah, but you guys can try that. You can just see that if the error also starts to increase after 10 to the power minus 4 only or not for the second order derivatives for a tan x or for any other function. Okay, because we can see that for the central difference it starts to increase after 10 to the power minus 5 only for both the functions, right? For the first order derivative, okay, let me just add a first order derivative and we can verify. Copy from here. Yeah, so this should be f, this should be f. Rest everything would remain the same, and exact derivative would remain the same. Error f, I guess, forward minus exact derivative 1. So this is for the central difference, and we will add 1 for the forward difference. Mhm. Shit. I closed the plot. Okay. Just plot this again. Log of h ref, and I will plot it using blue. Change this hold on to this place. Why is this giving me 0? X plus h minus fx, x is equal to 1. Uh, so for some reason it is giving me 0. For the central difference also it's giving me 0 after a decrease in h. So I will check that and think it's probably because it's getting really close to, but then the error should increase, right? Mm. For 8 and x, this is running fine. It's going for higher values also. Yeah, but I think probably this will also start to increase after 10 to the power minus 8. So yeah, for forward difference, the optimal h is 10 to the power minus 8. For forward and backward, for central difference, the optimal h is 10 to the power minus 5. And for the second order derivatives, for the optimal h is 10 to the power minus 4. Fine. Mm, okay. So any doubt in this? I will check why this is coming exactly 0 after these lower values of h. I'm not sure right now why this is happening. Fine. Other than that, any other doubt in this? Uh, so Anjali, I don't check the chat. You can just directly ask using microphone. It's simpler that way.
Okay, sir. Sir, I was asking, can we change the color of the graph lines from the graph window only?
Yeah, we can do that. So there is this cursor option over here. If I click on that, and then I can select whatever the thing I want, and I can just select this curve, right click, and then there is option for color. So I can, yeah, so pop-up opens and I can change the color. I can change yellow, green, blue, whatever I want. There are also other options. I can change the line style. I can change the line width. I can create markers. Okay, yeah. I can create markers. So plus point. So whatever things that we can do using the command using these commands over here, log like this, blue, green, R, all of those things we can do using this right click, right mouse button also. And then there are other options that can be checked using the property inspector. So if I right click something and open the property inspector, yeah, so there are the other things also which I can change. There are a lot of things, so you can go through
So, sir,
this.
will the command also change? If we
What?
make any changes in the graph, the command will also be changed.
No. So right now, if you make any changes to this graph, this will remain like it is. But if I run the code again, if I run this code again, then these command will override this graph. So if I run this code again, these commands will be plotted again, right? If I'm not closing the graph.
So, if we want to have changes permanently, so we have to do the changes in the commands only.
Yeah, you need to do the changes if you want to automate your code. Otherwise, I can do the changes over here and I can just save this as a figure file. And then like I can do a save as, and
We
I can
can
save
use
it.
this image in the command, na? So,
Uh, I'm not sure what you mean by that. Image in the command mean?
means if we save this, we can use it further.
Yeah, you can use it further. So if I just do like so I'm saving it as a MATLAB figure file. Uh, Now if I okay, let me first see if it has saved or not. Yeah, so you see there is a test figure command. So now if I close this, if I run this command again, then this the graph which will be generated using that will be using these line of commands only, right? So I will get the similar the previous graph only. But if I open this saved figure file, so this will be the figure that I saved. So now I can again edit this figure in whatever way I want. Okay.
So, sir, how can we incorporate this new figure in our command?
No, so this figure is being generated through command. We are not the whatever changes we are doing over here, we are not writing any command for that. So they are not being reflected over here. If you want to do automate this using command, then you need to write commands over here only.
Okay, sir. Thank you, sir.
Fine. But you can save the figure, and then afterwards I can just I can get a axis handle of this. So you can check on the MATLAB help or MATLAB documentation. I can get axis handles for these axes, and I can get handles for each of these curves also. And then I can edit those axes, those handles using this command window itself, other than selecting this and doing editing it. But I find it like if you don't want to automate the graph, if you have to make only certain small number of changes, then these manual tuning, it's much better than writing the command. Okay.
Okay, sir.
Fine. So this is clear to everyone. I will just move to the next part then. That is, yeah, so there is one more example. So we can check this also. This is similar. So I've already created a function for that, I think. Yeah. So Arrhenius equation. This is similar to what we have done previously. I'm just using a function handle to create this function, and then I'm taking derivatives using first order and second order derivatives using central difference method. So this is for the first order derivative. This is for the second order derivative. These are the true values. So this is an exponential function. So this part of the function will remain the same. These two part will remain the same. I will just, for the first order derivative, I will just get a minus e by r upon t. So that is what I'm getting over here. Uh, yeah, and similarly, I will be doing this differentiation again. So this is like my RT only, and this is what I will be getting for the second order derivative. This is the first order derivative only. Fine. So this is the error, and I'm just displaying that. So this is like a similar command. So my error, which one? Yeah, the last one is my error. So you can see I'm getting small error values. What this function was implying is that we do this for different values of h. So like similar to what we did over here, we can create a vector of h, and then we can try to we just need to make changes over here for this different values of this, like for this vector h, we just need to do element wise operations over here, and then it would be fine. So we can do that, and we can check after this, like the optimal h value would be 1/3 of the machine precision, like cube root of the machine precision that is there. Okay, so if I check this, yeah, so this is, sorry, 1.3. Yeah, so this is my machine precision, and my optimal edge should be somewhat closer to 10 to the power minus 6 only. Okay, so you guys can do this. I can change it over here. Okay, which one was that? Yeah, this is only right. So I can just change my x over here. Copy this edge. Mm, let's go till 8. I am removing this because this is a scalar value, single scalar value. It will give me an error because other two will be a vector then. So you can't concatenate different sizes. Yeah, and I need to multiply it by the absolute value of temperature. Okay. Uh, Let it be like this, because otherwise, yeah, first let us do it like this only. Yeah, I'll plot a log plot of h versus starter derivative only. Oh, okay. So this should be a vector, and this should be fine, and this is a scalar multiplication. This should be fine. Yeah. So again, like 10 to the power minus 8. The optimum is 0.01. I could not just standard derivative. The error remains approximately the same. Then it starts to increase after so the error starts to increase after third derivative itself, after the 0.001h itself, and for the second order derivative it starts to increase after 10 to the power minus 5 minus 6 itself. Yeah, 10 to the power minus 5, and for this it starts to increase after 10 to the power minus 3 only. But if I look at yes, minus 1 by 3. So this is 10 to the power minus 6. Something is happening. No idea what. Is it giving me error? Minus C upon RT. So if I differentiate this, Kc exponential u minus 1x minus minus plus, this is fine. This is fine. This is fine. So here there is the optimum h should be 10 to the power minus 6, 10 to the power minus 6, yeah. But for now, this is not coming at like that. this last time. Because I will check this and I will update the PPT. Yeah, but this should be like 20. I will check and update the code because some error is there. It should the optimum should be around 10 to the power minus 6 only. This was running fine when I last did it and did this. I think I made some errors somewhere. I don't know what. Uh, yeah, fine. So I will update the code and you guys can see the code then. Let us go to the next part, which is the partial derivatives. Yeah, so we have this function x, which is a function of two variables, x1 and x2. We will be so we need to find the derivative of this function with respect to x1 and with respect to x2. So similar to forward difference, like similar to what we have been doing until now. For one case, we will be just disturbing one variable while keeping the other constant. Like if I'm trying to find the derivative with respect to x1, then I will just think, yeah. So this is for the we can check it over here also. In this case, if I want to find the derivative with respect to t, so I will in this rate equation I will just minutely perturbate the variable a1, or in this case variable t, little bit forward and little bit backward, as we are using the central difference. And when I am trying to find the partial derivative with respect to c, so I will perturbate the second variable while keeping the first variable constant. So this like the second vector, this is my perturbation. So I'm in one case I'm making this first row 0, while the second row is a constant number. And in the first case I am making the second row 0 and the first row is a constant number. So I will be perturbating the first variable in this case, first case, and I will be perturbating the second variable in this next case. Okay, so first we will be doing the same thing for this function also. In one case we will be perturbating the variable x1 keeping x2 same. In the other case we will be perturbating variable x2 keeping x1 same. Okay, so let us check this. I think, yeah, this is the one. So this is my function handle, x1 x2 sine x1 exponential of x2. uh, I will be doing this for two values of x1 x2, so x1 1 and x2 2. My h value would be 10 to the power minus 3. This is my using central difference. I am taking partial derivative of x1. So in this case, you can see like I am passing the function handle, these variables to the function handle. So I'm just changing perturbating x1 with a small amount h. There is no perturbation given to x2, and in this case also I'm reducing x1 by a small amount. There is no changes to being made to the x2 variable. Okay, in the next case I am making no changes to variable x1 and I am slightly changing x2, and here also I'm slightly subtracting h from x2, making it little bit smaller than x2. Okay, my true derivatives are these two values, and yeah, this is my error. Okay, so any doubt in this, like what we have done, why we are perturbating only one variable? Okay, so if I run this code, okay, so yeah, um, so this is the partial derivative. These are the true partial derivatives, and this is the error. Okay, so our error is of the order 10 to the power minus 7, right? I need to make one out. Yeah, so our error is of the order 10 to the power minus 6. Our h is like 1e minus 3. So central difference has the error is like of the order h square, right? So if I'm taking h to the power 10 to the power minus 3, so my error is like 10 to the power minus 6. Okay. Uh, Fine. Uh, Now, if I want to do the same thing with the rate equation, so I will just change this function over here with this rate equation, and rest everything will remain the same. Okay. So you can, I don't think I have that over here. Yeah. So you can try to do that. It's simple. Anyways, I will give you these files so you can edit these files only, and then if you have any doubt, you can always ask in the next class, or just I think now since we are using Teams, so all of you guys can access the chat of this team at all times. So you can just message over here also. Fine. Mm, yeah. So this is the partial derivative. Now let us go to the numerical integration. So what basically we are trying to do is we are trying to find the area under the curve. Uh, Usually what we do is like if we have some curve. So the simplest method that we can find is like if I have the function values at these points. These lines go there. Yeah, so we can approximate these using these rectangles, right? So the area of this rectangle would be whatever this distance is. The distance between the 2 points. Suppose this is 0.2. And then the function value at this point. So we will get this shaded rectangle as one area. Then we go to the next point and we get this shaded part as the next area. Then this part as the next area, and we all add up all these areas. So this is the simplest method. But what will happen is that we are missing these regions, right? So every time we are missing the area being captured by this region, right? So this leads to the error, right? So every time the missing information, it adds up, and eventually we get a very large error, right? The development over this is the trapezoidal rule. So instead of just evaluating this, I think I should have that on the next slide. Yeah. So instead of just evaluating these different points using, I don't know why this goes over there. So instead of like this, right? So instead of evaluating the entire thing as these rectangles, we try to approximate them using trapezoids. So right now, if I'm just distributing it in 2 points, so I will be, if I would have using the rectangle method or the simplest method, then it would be like this, right? So this is the area that I would be getting. I would be missing on this much of the area. But if I'm approximating it as a trapezoid, so I add this triangular portion also over that rectangular. So it's much better approximation than the rectangle, but it's still it's not close enough to the close enough to the exact uh, shape of the curve, right? Uh, yeah. This is what the formula, like if I try to find the area of trapezoid, so area of trapezoid is the um, sum of the two parallel sides multiplied by the distance between them and divided by 2. Okay. So this is like the distance between the 2 points. So this is my h. This is the length of this line. This is the length of this line. Okay. So it will be like f of a and f of b. So the sum of two parallel lines, two parallel sides would be fa plus fa plus f of a plus h. Okay. So this is how I get this formula for the trapezoidal rule. Now, in this case, like if this is my point A and this is my point um, B, okay. So I am approximating my B with H, right? So my A plus H would be my B, okay. Like my yeah. This is my FA point, this is my FB point. So I'm writing my B as A plus H, right? So my H would be B minus A. For the single, like if I'm approximating the entire curve using only 2 points, in that case my H would be B minus A. Okay, and the order of accuracy for this method is like H cube. Fine. Uh, Let us just check one example. Okay, so I will. Yeah. So this is my function 2 minus x plus ln x. It's a same function what we did in this. Okay, yeah, in one of the cases, differentiation cases, we did this function. Yeah, so this is the same function. My order of integration, like my limit of integration, is from a is equal to 1 to b is equal to 2. Okay, this is the exact or the true integration of this function, and I've just created a function handle for that, so that in if I want to change this a and b values, then it is easier for me to again recalculate the true integration. Okay, so this is the true integration value. I just pass on the b and a values to this function handle. I'm subtracting that. So this is my true integration value. Now my for the trapezoidal rule, my h value would be b minus a. I'm just approximating the, okay, let us first plot this, right? So that we can see what we are getting. So let me first create this function, and from 1 to 2. I hope I don't have any plot of them. Yeah. So I will plot this, and f of x. This should be a vector. This should be a vector. This is a scalar. It should be fine. Yeah. So this is my function from 1 to 2. Okay. And if I'm using a trapezoidal rule, so I can annotate this. Yeah. So if I'm yeah. So if I'm using trapezoidal rule, okay, let me, how do I? I need to change the limit of the y. So this graph is from 1 until 1. Okay. So I will make this limit from 0 to 2 or 1.5. Now it is better. So now if I'm approximating it using trapezoidal rule, so I will be using some, sorry, is there a way to make a straight line? Hmm. Yeah, so I will be approximating it like something like this. Okay, so I will be missing out on this much of area, this area, right? If I'm using the trapezoidal rule. So let us first do that. Start interacting with the background. Yeah, so I will first run this part. Sorry, first run this part, this section. Yeah, so my h is b minus a. I am taking my x from, so like in this case I will be only getting a two way, x would be the 2 cross 1 vector, so it starts from a and goes to b. H would be like 1 only. Yeah. I'm evaluating my function, this function f at those x values. So this f val would be a 2 cross 1 vector, 1 cross 2 vector, and then I'm just adding those two function values and multiplying by h by 2. Okay, and this is I'm calculating the error. So I will run this section. Yeah, so the first one is the value that I'm getting from the trapezoidal rule, and the second one is the error. Okay, so I am missing out on 0.04 of the total, no, like 0.04 of the total area. Uh, and this is okay, let me also plot the true value. So this is my true value, 0.8862. Okay, fine. Now let us see the next rule, which is improvement over trapezoidal rule. So in this trapezoidal rule, we are sort of approximating the function, this function as a linear line, like with the end two endpoints, we are joining it like a linear line, using a linear or using a line. Okay. In this, the next one is the Simpson's 1/3 rule, where we take another point which is in the midpoint of those 2 points, and then if you go through the derivation of Simpson's 1/3 rule, you will find that in this case we are approximating these 2 points, these two endpoints. We are joining these two endpoints using a second order polynomial. Okay, so we are joining it something like this. So since we have, so we need one more point in between. Okay, that is why this midpoint also comes. Like we have second order equation is like y is equal to ax square plus bx plus c, right? So we have three unknowns a, b, c, and we only have two equations, right? So we need one more equation. So that is why this third point is also coming. Okay. Uh, we'll use this for annotation. This is much better. You can use Control Z to go back. Yeah. So in this case, we are approximating this using a second order polynomial. So we need 2 points for approximating it. So that is where this third point also comes into the picture. The formula would come out to be fa plus 4 times of fa plus h plus of fa plus 2h. And then we multiplied by h by 3. Okay. Uh, so now this is our b, right? So for this like single case only, we are approximating the entire curve using only 2 points. So if I equate this to b, then I will get the value of h as b minus a by 2. And the order of approximation is h to the power 5. So this is much more accurate than trapezoidal rule, or trapezoidal method. Okay. The next one is Simpson's 3/8 rule. So this is an improvement over the 1/3 rule. In this case, we are approximating the entire curve using a third order polynomial. So we have like ax cube plus bx square plus cx plus d. So we have 4 unknowns. So we need 4 number of points, right? So which is why we take 4 points in the Simpson's 3/8 rule, right? And we evaluate the function at each of those 4 points, and we get this formula. Okay, so fa plus 3 times of a plus h, 3 times of a plus 2h, and a plus 3h, and then we multiply it by 3h by 8. We evaluate this last part to b, like equate this last part to b, and then we get the value of h as b minus a by 3. The order of approximation is similar to the 1/3 rule, h to the power 5. But we get much better results because like we in this case like we are still missing out on some part of it, but in the 1/3 1/3/8 rule we are also like we are approximating the curve using a third order curve, so it's much better approximation than a second order or a linear curve. Okay, the other thing to note is this is like I'm going from a to a plus h to a plus 2h. So like we will have how much even number of points in between, right? Like a plus 0, a plus h, a plus 2h. So I need to have two number of subdivisions. Like I need to have two number of subdivisions, including the end point, right? So in total, I need to have in this case, like I am approximating this using only 2 points. So I need to have the first point and then two other points. In Simpson's 3/8 rule, I need to have the first point and three other points, right? So the total number of divisions in this case would be even number or a multiple of 2, whereas the total number of subdivisions in Simpson's 3/8 rule would be a odd number or a multiple of 3. Okay, so we can easily see that using this formula to calculate h. So in this we are dividing by 2, so we want our h to be a multiple of 2, whereas in this case we want our h to be a multiple of 3. Okay, fine. We'll stop the annotation. So any doubt in Simpson's this rule, 1/3 or 3/8 rule?
Hello.
Yes.
Sir, as you told in trapezoidal rule, trunk error is in that is order of h to the power 3. In Simpson 1/3 rule, order of h to the power 5. Sir, what
Yeah.
is actually mean of this? I am confusing.
Okay, so the smaller the value of h you take, the much better your approximation would be. Like in this case, our error would be if I take like h 0.1, okay. So my error, the minimum error that the maximum error that I would get is of the order 10 to the power 3, right? So if I am taking my h as, I will just annotate it. Yeah, so if I take my h as 0.1, then order of h to the power 3 would mean that my maximum my error can go is to the order to the value of 0.001, or my error would always be less than this value. Whereas for the Simpson's 3/8 rule, uh, for Simpson's 3/8 rule, my order is h5. So that means if my h if my h is 0.1 itself, then the maximum value of my error would be like 10 to the power minus 5 only. Okay. Is this clear? So that means like I'm my error bound. This basically gives me my error bounds. So for the trapezoidal rule, my error bound is a higher value, and for Simpson's rule, my error bound is a lower value. Okay.
Sir, one more doubt is there.
Yeah.
Sir, why we find H? We simply applied formula and get result. Why we need to find H?
Which H are you talking about?
In which you say order of h to the power 5, then
Yeah.
why we need to find it? We simply apply formula and get answer.
So yeah, these error bounds, we basically use these error bounds to know how accurate our result is. Like for the problems that we are trying right now is like simple cases. We can easily calculate the true value, and we know that okay, this is our true value. This is the numerical value that we are getting. But for other big harder problems, it's not always easy to find the true integral or true value of the integral. So this order, it basically helps us to get a maximum bound on how much error our approximate integral is having. Okay.
Oh,
So
and
if you go to a
yes.
proper numerical computation course, like this is a MATLAB programming for
Yes, sir.
numerical computation. If you go to a numerical computation course, there for each of these rules like trapezoidal Simpsons or one third or three eighth rule, if you go to the derivation, then there are error bounds also. So what is the maximum and minimum error that you should be getting if you are using these formulas? So we use these order like H5, H3, we use these orders to get those error bounds. Okay, so they help us
Uh,
know how accurate our result is for harder problems. For the simpler problems, it's easier. We can easily calculate the true value. Okay.
so, sir, then which rule should we recommended for upcoming problem or in the future? Like,
Yeah. So basically, right now, if I mm, if I look at the inbuilt MATLAB functions also, like the integral functions which MATLAB has, so they
yes, sir.
use an adaptive Simpsons rule like for
Uh,
1D problem. So basically they use adaptive Simpsons rule. So adaptive is like in the sense the H value, they change this H value based on the tolerances. So right now we are using a constant H value for all the points. What they do is to continuously adapt these H values on for different intervals. Okay. So like between these 2 points, if I have like points like this, so between these 2 points, they use a different value of h, and then between these 2 points, they use a different value of h and different value of h. So they adaptively change the value of h. The formula remains the same, but they adaptively change the value of the h. And then there are in this integration formulas like Gauss quadrature and Riemann integrals, things like that. So I think you need to take a proper numerical methods course to get into those formulas. But there are better approximations also. Gauss quadrature is one of them.
uh, okay, sir.
Okay.
Okay.
Yeah. So we will just Okay. I will close this. Should be a method to clean this screen also. Yeah. So if I look at the one third rule. Yeah. So like this is the Simpson's one third rule. I am calculating my h value as b minus a by 2. And then this is just simply the formula. I am passing the a plus h and a plus 2h values to the function handle, and I'm multiplying it by h by 3. And now if I run this part, so you see the my true value is 0.8862. This is 8858, and this is the error that I'm getting. Okay. Uh, yeah, so in this case, my h was 1. Okay, so this is like h cube. So uh, it's like 10 to the power minus uh, 10 to the power minus 2, in the range of 10 to the power minus 2 I am getting. In this case, my h is 5 into 10 to the power minus 1 in the one third rule. Okay, so I'm getting in the range of like 10 to the power minus 3, right? My Simpson's rule is giving me a much better approximation. Now, if I use the Simpson's 3/8 rule over here, so I think I had written the code for that also. I have not. I think I removed it. I had written the code for that also. Uh, yeah, I think I have removed it. So I will just write the Simpson's 3/8 rule also. Um, my h would be b minus a by 3 and 2 3 into h by 8 multiplied by what's the formula? What's the formula? 3 3. And I will plot. I will just display. By a tool will be I sim 2 and error sim 2. I think that's the name. I will run this part. Yeah, so here the error again decreases. There is no change in the order, like it's still 10 to the power minus 4 only. But since we are approximating it using a third order polynomial instead of a second order polynomial, so we get a much lower error, like compared to the 1/3 rule. Okay. Mm, yeah. Then this. Okay, so this is same as that. I made multiple programs. I don't know which one is which. Mm, yeah. So now we just try to integrate this function. So the program will remain the same. I just need to, instead of having, yeah, so in this case, I had, I'm getting confused with my own codes. Mm, this is for the inbuilt function. This is for the inbuilt function. Yeah, so this is the one. So if I now, yeah, so your question was like how to choose the value of h, right? So we can simply plot for different values of h. Right now the same code, the same function. I am using different values of h. So yeah, this is the multi-case problem. So if we go into the multi-step integration, right now what we were doing is we were trying to approximate the entire curve using only these 2 points, right? But if we approximate them using multiple points, so we will have these like divide those points into multiple. Yeah, so okay. In this case, what we were doing previously was using a single point we were trying to approximate, right? But now if I choose multiple points, like this, and then I try to approximate each of these points using one trapezoid. कभी सीधी लाइन बना देता है, कभी कभी नहीं बनाता. Yeah, you get the idea. Uh, yeah. So now if we are approximate is using multiple trapezoids. This. So in earlier case, we were losing this area, right? But now if when we are approximated using smaller multiple trapezoids, so we are getting a much better linear approximation of this non-linear curve. Okay, so we are only missing out on the smaller areas for each sub part, right? So we get a much better approximation as compared to the single point approximation, right? So yeah, so if we look at the formula, so for the first part, using trapezoidal rule, we get this f h by 2 fa plus h. For the second, we get fa plus h, like this is my a plus h point. Now this is my a plus 2h point. Then this is my a plus 3h point, and likewise this is my a plus nh point. Okay. So I get a series of smaller areas like this, and then I can simply add all of this together to get my total area. So if I try to add all of this together, so this first point and this last point, they only appear once, right? This point and this point, they only appear once. Rest, when I'm calculating this area, so this point appear once, then I'm calculating this area of the second region, so also this point appears. Then similarly from 2 to 3, this point once appears in calculation of area 2 and once in calculation of area 3. So all the other points we are getting two number of times, right? So if I add all of these together, so I get this formula h by 2 fa once and fa plus nh once, and rest all other points I'm getting two number of times. Okay, so this is the formula for the trapezoidal rule for the multi-step integration. Okay, any doubt in this part, the multi-step for the trapezoidal rule? No? Okay. Then similarly, we can get the formula for Simpson's 3/8 rule. So I write this like the first integration as this h by 3 fa 4a plus h, a plus 2h. Then for the second part, I get this, and similarly, likewise, I write for the last part. Now, when I try to add, so my first and my last point, they only appear once over here and over here. Then a plus h appears like in the first one, it is 4 multiplied by 4. So it appears like 4 number of times. Then this one does not appear in calculation of the second point. So what is basically happening is that I am so I'm combining this one part together, these 3 points together, and then for the next one I'm combining this one. Yeah. For the next one, I'm combining these 3 points, and likewise. Okay. So for the calculation of the first one, this point is like included 4 number of times. This is once, this is once. Okay. When we go to the next one, so this point is included once, this point is included once, this point is included 4 number of times. Okay. We can see the pattern, like all the points odd, which are odd, they are being included 4 number of times, and all the points which are in even multiples of h, they are included 2 number of times. Okay. So we can write this final formula h by 3 multiplied fa and fa plus nh one number of times, and all the points which are even multiples of h, we add them together and multiply them by 2 because they occur twice, once for calculation of each subpart, and then with odd multiples of h, they occur 4 number of times. Okay. Fine. So this is the formula that we get for the Simpson's 1/3 rule. Okay. You can similarly calculate the formula for the Simpson's 3/8 rule. This is that's also simpler. We just need to write two or three of these terms together, and then we can see the pattern, how many times each point is occurring. So in that case, we will be including 4 points. Okay. So in 1/3 rule, we were including all of these three together. In those, we will be including all of these 4 points together to calculate the area of one subsection. Okay. Fine. So we will just see a short code for that. Uh, yes, first let us see it for the. Okay, first let me just do it for n is equal to right now. Earlier we were doing it for n is equal to 1. So we were getting something like this. Okay. So let me just do it for n is equal to 1 and n is equal to 2. Okay. Explain the error also, right? Yeah. So I will clear this CLC. Yeah. So with 1 point, I am getting my error as 0.03. And if I'm just adding one more point with n is equal to 2, my error reduces by 1/4, right? So this is like close to 4 and this is like close to 0.1. So my error reduces by 1/4. Now if I add one more point, my error again reduces to 1/4. 1 and then point 0.004. Yeah. So mm, close to one, close to twice, right? Yeah. So my error again reduces by half, like close to half. Hmm. So likewise, if I keep on increasing points, my error keeps on decreasing. So it again becomes half, right? Yeah. So this was like 0.04, then it became 0.01, then it became 0.04, 0.05, then it became 0.025. Okay. So if I plot the, okay, let me just do the first one. I will take these multiple values of h and I will plot this. Yeah. So you see, the more number of points. So this is basically a log plot, but instead of making the scales as log values, I have kept them as normal scale, normal linear values only. Uh, yeah. So this is like for the, this is my h value, right? So the larger my n value is, the smaller my h value becomes. So this one is for n is equal to 25. Uh, and this one is for n is equal to 2. Okay. If I try to get the slope of this, then it should be like close to 2, because that is what we are seeing here also, right? Each increment of point, my error is approximately reducing by half. So if I try to calculate this, mm, mhm, mhm. So what I will do is, there is this method called g input. So I will just use that to get my points. Okay. I need to add a 1 over here. So this is one of the point. Similarly, I can get the second point. And now if I try to plot the error, so that would be like x2 to, oh, not the error, sorry, the slope, minus x1 2 divided by x2 1 minus x1 1 x1 1. Yeah, so this is like close to 2. Okay, which is similar to my I think I missed one slide. Yeah. Um, so this is like close to 2. So with the each increment of so my overall global global approximation is like of the order h square, which is one less than the local truncation approximation, right? So in the lectures shown by the professor, I think it's not in here. Yeah. So you see, the local truncation error for trapezoidal rule is like h cube, and the global is like h square. So that is what we are seeing over here also. The more number of points we are increasing, our error, the we are reducing like h. We are the more number of points we are adding, we are reducing h, and then the order of approximation is becoming like h square. So the slope of this graph is also twice. So the more number of points we increase, we are reducing our error like by half. Okay. Yeah. So this is the thing. Then there is one more example, which I think I have also coded somewhere. Yeah, so this is the one. But before that, let us look at the two MATLAB functions. So the first one is trapz. If I try type help trapz, okay. Why is it taking this long? Okay. So we have like three different types, three different inputs that we can give to this function. The first one is like if we just simply give the value of the integral y, then it takes the value of x from 0 to 1, and then it evaluates that integral. Uh, if we want to change the limits from 0 to 1 to some other value, then we just need to multiply this z by the spacing increment and whatever the spacing increment we want, and then it will calculate that. It will give us the values for those increments. Okay. Uh, then there is x and y, in which we give both the x vectors and the x value of a vector of x values, and then the corresponding y values for this corresponding x values. Okay. Then there is xy and dimension. So integrates across the dimensions, like in which if both x and y is like a matrix that we are giving, and then so in that case we can give another dimension, like we want to integrate across the rows, or we want to integrate across the columns. So then it will output us a vector with each element being the integration across the dimension, across the column or the row, which whatever we have given. Okay. So yeah, so let us just look at this. So we will be solving this example using the first we will just use it solve it using the formula for the trapezoid method, and then we will use the trapezoid function, and then we will see what values we are getting in both the cases. Okay. Uh, yeah, so this is my function. So this is like my function handle. I know that my x would be a vector, so I'm already done element-wise multiplication operations over here. Then a is 0 and b is like the upper limit is conv, so that is 0.5. Okay. If I run this section, fine. Uh, so first I will take 10 intervals, and then I will evaluate it using the trapezoid rule. I'm using n is 10, then my h will be b minus a by 10. I am creating an x vector starting from a in increments of h and going to till b. Then my f vec would be like it's just I'm passing this x variable to this function handle. I'm getting a vector of the values at those those x values. This is like my formula. So this multi-step formula. Yeah. So this multi-step integration formula. This is my first point, first element of the vector. This is the last element of vector, and this is like okay. Okay, sorry, I am talking about the one third rule. Yeah, so this is the first element of my vector. This is the last element, and this is I am taking a sum from the second element to the second last element, and I'm taking a sum of that, and I'm multiplying it by 2. So similar to what I'm doing over here. Okay. And then I'm also evaluating the same integral using Simpson's one third rule. This is my first element. This is my last element. And then I'm taking the sum of all the odd elements. But here, like the MATLAB array starts like from one and then goes 1, 2, 3, 4 like this. It starts from one. In some other languages like Python and C++, the array starts from 0. So it starts from an even number, but in MATLAB, it starts from an odd number, right? So that is why these increments of a plus h, like the odd increments of h, uh, I am here taking as starts from 2 in increments of 2 and it goes till n minus 1. Whereas the even increments of h, like this 2h n minus 2h, 2s 4h n minus 2h, these starts from 3, an odd number, and goes till n minus 2. Okay. Any doubt in this? Like this is different than what is written over here, but it's only because MATLAB the first index starts from one, an odd number rather than an even number. Okay. So no doubt in this part, right? If you have any doubt, you can ask, or you can try it yourself and then you can ask. Okay. Uh, yes, I will run this part. Then yeah, so we can see over here that trapezoid, we need to output the x values. we need to input the, yeah, we need, okay. We need to input the x values as well as the y values. So I am inputting my x vector over here and the corresponding y vector, or the function values vector f vec, okay, to this trapezoid. Similarly, I have a quad function. So this trapezoid function uses the trapezoidal rule. This quad function, this uses a, if I type help quad. So this uses an adaptive. We go over here, yeah. Mm. Numerically evaluate integral adaptive Simpson quadrature. Okay, so this the adaptive Simpson quadrature basically means that on the h function, it tries to change the h value adaptively based on the tolerances, that inbuilt tolerances or the function that we have given. Okay. So in this, the first one is that we need to, the simplest input is the function handle and the upper and lower limits, lower and upper limits. A is lower limit and B is the upper limit. The other one is the tolerances. Okay, so what tolerance we want. Uh, then to meet these tolerances, the function will change the increment or the h value adaptively. Okay. Then there are other things also. With non-zero trace shows the values of FCNT A, B minus A and Q during the recursion. Uh, yeah, so like it tries to run this, the entire program runs in a loop. Like it checks for some h value, then calculates the then checks the tolerances, and then it again changes the h value and then calculates the entire integral, then check the tolerance. So for each of these value, what the q value is, like we can get all of that also as the trace of the overall function. Okay, so this trace is basically a log of this function, what this function is doing. Right, so we will just use the simplest one, the first one. So we will input the function handle f. So this is this function handle, and then the lower limit a and the upper limit. So the a value is 0 and the p value is 0.5. And then we will evaluate this. So we'll evaluate this and then we will output the results. Okay. So the first one is from the trapezoidal rule. This is from the Simpson's rule. So we can see, and then this again is from the trapezoidal rule. Okay, let me just make this short. Yeah, so now it's much better. So you can see that trapezoidal rule and the trapz inbuilt function, it gives us the same value. You can see also over here, both of these function gives us the same value. The trapz also does not changes anything adaptively. It just trapezoidal numerical integration. So it for the simplest case trapz y, it uses a unity spacing. For this trapz x comma y, we already give the spacing ourselves, so it is not changing anything inside the code. For this also it is not changing anything inside the code, right? So we are getting the same value which we are getting using our own function, and the value which we are getting using the inbuilt MATLAB function. The Simpson quadrature, the Simpson one-third rule, and the Simpson this quad function. So the adaptive Simpson quadrature, we are getting somewhat different values because we are the quad function adaptively changes the h value, which we are not doing for the one-third rule. Okay. Yeah. So this is the case with these different functions. Okay. Uh, I think. Hmm. Okay, so mm, okay, so what do you want me to do? Do you want me to solve this assignment, the non-grade assignment, or I have some problems, so or we can solve these problems? Which one do you prefer? We still have around, I think, oh, we are out of time. So I can just take 10 more minutes of you and I can give you a short summary of what you need to do. Okay. What do you want to do? This or the assignment, non-graded assignment?
Hello.
Yes, Aditya.
Yes, sir. You we can solve assignment if time is.
The non-graded one. Fine.
Yes, sir.
So I will just go to the site. Yeah, so this is like similar to what uh okay. So we need to use the central difference formula. Fx is this. Fine. So I will just use any of them. And I will copy everything actually. Then we will change whatever we don't need. Um, Fine. So we just need to change this to this 1 by x minus 10. So 1 by x minus 10 plus 0.87 to log of 6 plus 25 by x6 plus 25 by x. Fine. Uh, the true value is given to us. Okay, let me change that also over here. So 1 minus x is square, 1 by x is square, uh, minus what is it, 1 plus 25, 21.75 divided by 6 plus 25 by x. Fine. We don't need the forward, and so I will comment this out. So we need to please report the approximate value of at x is equal to 0.25 using h is equal to 0.01. So this we need to change to 0.25 and h would be 0.01. Okay. So I just changed this function handle to the function value which we are given. I changed the true value and then rest everything is same. Exact derivative. I will just add it over here only and then f central. Uh, yeah. So this is the exact one, and this is the which I'm getting using this value. Okay. So I will just mark this minus 19.3105. Also report the error. So you can get the error. Well, minus of central. So our error is 0.0275. 275. Please report the value of h for which the error is minimum. Also report the minimum error. Yeah, so you can simply make this for different values of h. I will just copy from here. Yeah, so I need to make this function, or do I need to make? Yeah, this is fine. Yeah, so actually we are passing h as a vector, so this needs to be element wise, and this also needs to be element wise. Okay, because h is a vector, and here we are passing x plus h, so this x plus h would be a vector. Okay, so this needs to be element wise. This is yeah, this is fine now. And this should be element wise. This is fine. It's scalar multiplication only. Now this true value, we need not to output this because this is a single scalar value, so we might get in concatenation, we will get in concatenation error. And this h is, they want us from -3 to -8. Okay, so I will just make this -3 up to -8, and I will plot. I can simply see this error, and in here I can put this h. So I can get h, f central, and error. This need to be column vectors. So if you have any doubt, like whatever I'm doing, you can just simply ask. Okay. Uh, Anyways, this is simpler. Like what we have done, I'm just changing the codes, previous codes only. Let us plot the error itself. So this is my minimum error. Then it is again it starts to increase, right? Why is that? Okay, let me plot it on log h comma error. Yeah. So like 10 to the power -6 is my minimum error, and then again it starts to increase. Okay. Yeah, so 10 to the power -6 and minimum error. So this is like, how much is it? -11, right? 3.6 into 10 to the power -11. 3 into 10 to the power -11. You can search somewhere. Okay. Okay. This is the Simpson's rule. So you can change any of these function files. I will be giving you these function files. Like I can copy this part. Problem 1. Problem 2. I need to just change this fx to x square plus 1 exponential 1. This will be like x square plus 1 multiplied by exp x. My system hangs sometimes. It starts from 0, goes till 1. The true value is 2e minus 3. So this is constant. Yeah. E is predefined variable in this. I think xp1, just try txp1. So we have to use an h value of 0.05. First, we need to use a single application of Simpson's one-third rule. Okay. But still, since we need to have h value of 0.05 and this is from 0 to 1, so basically this means it's a multiple integration sort of application. So I will copy something from the multiple. Yeah, this should be good enough. Uh, we don't need n. Since we will be doing this for the multiple cases, so this x I would pass as a vector. So this should be element wise because then or not. Okay. So for the first case, our h is just 1. So true minus. So I will run this section. Yeah. So this is what I'm getting. So report the integral below. So it would be like 2.1455. 2.1455. Okay, let us check the true value also. So I true is 2.43. Okay. Also report the absolute error, that would be 0.291. And then with 0.05, so I will just change this h value to 0.05. I will run this. So now my true value is 2.4365. And my absolute error, that is like 0.00000010. 5 zeros. Okay. Uh, this is simple. This is simple. Uh, should I do the others also, or yeah, I think they are simple. I will just check the answers to the first four. Correct, correct. Okay, so this is correct. This is correct. This is correct. This is correct. Why is this not correct? Uh, use the single application and report the integral. What did we do wrong? The others are correct. Which is equal to 1. Hmm. So probably this is giving me some. Okay, but I'm starting from 2. Not with any difficulty. Yeah. So yeah. So what the error was like? For single point application, if my trapezoidal rule would have been there, then my h would have been 1. Like it was simply b minus a by 1, right? But this, since this is 1/3 rule, so we need at least 3 points. When I was doing it like 1, so I would have I'm only using 2 number of points, right? So if I do this, then my x would be yeah, so my x would be like 0 and 1 only. I need 3 points for the Simpsons 1/3 rule, right? So this should be like b minus a divided by 2. So like 0.5. Now if I do it with 0.5, then I'm getting this 2.446, right? So that is like my correct answer, 2.446. And my error would be like 0.0101. So this would be like 0.0101. Okay. Now if I just check these two, yeah, so now this is fine. So that was the mistake we were doing. I was doing. Uh, this is, we just simply need to evaluate using quad. So we even need not to make any function. Problem 3, we can simply create a function handle. x to the power a plus 1 exp1 plus 1 multiplied by exp of, is it 1 or x? It's x. And I simply need to write z is equal to quad f and 0 to 1. That's it. Display z. Yeah, this needs to be, this is fine. This needs to be element wise. Yeah, so this is with a is equal to 1, 2.7182. And they want you to download this file and then do it. Otherwise, we can just simply create a function handle, and then we need to do it using a is equal to 2. So just change this to a is equal to 2 and run this section. So I am getting 2.4365. Check this. Yeah, so this is correct. Rest is also like similar. So we just need to create one more function handle, and then we need to use the trapz function. So since we are doing it from 0 to 10, first one is just a single application, so just 2 points, and the rest, and the next one is step size 0.01. Okay. Problem 4 is, okay, just is everyone getting this, or do you have any doubt whatever we are doing?
There is no doubt, sir.
Should I continue, or is it fine? You guys can do this, it's simpler. I will just do this
Sir,
last one and then
by myself.
yeah, fine then. So I'll just do this last one and then you guys can do it. First one, which is equal to we'll just write A as 0 and B as 10, and then my H would be B minus A. So my X would be A H B, and my F vector would be F of X. So I just need to make sure that these all are element wise operations, which I think yeah, it should be fine. So for the first case, I just need to use trap Z, X and F back. Display Z 23.66. Then I need to use H as 0.01. So I can simply write this as 0.01, 0.01, 0.1. I will run this. I'm getting 32.35. So yeah, so you can see how much error we are getting. So we are integrating from 0 to 10 only, but while using single point, we are getting our answer as 23.66. And when we are using like 100 number of intervals, then we are getting 32.35. So approximately an error of 9 points. Okay. The last one is actually very simple. So you guys can do this. What I wanted to discuss is yeah, so if we look at this problem, so we have an interval of 0 to 1. We know that for trapezoidal rule, it does not matter. So we can use any number of interval. In this case, it's like 0.2. But for Simpson's rule, so for Simpson's one-third rule, it's like a plus h, and a plus 2h. So the interval should be even number of intervals, right? So that is why we are using our h as 0.25. So we will have four number of intervals in between, right? Similarly, for Simpson's 3 by 8 rule, it's like a plus h, a plus 2h, and a plus 3h. So it should be a multiple of 3. The number of intervals should be like multiples of 3. Okay. Uh, so that is why we are using an h value of 1 by 6. So if I divide it like 0 to 1, and I'm dividing it in 6 number of intervals, which is a multiple of 3. So like 0, uh, 1 by 6, 2 by 6, and 3 by 6. That would be my one Simpsons integration, one part of the Simpsons 3 by 8 rule, and then 3 by 6, 4 by 6, 5 by 6, and 1 or 6 by 6. That would be the second part, right? Yeah, so that is why we are using it, even number of multiples of 3, and similarly in this multiples of 2, or even number of intervals. Okay, for trapezoidal rule it does not matter. So you can do this. Just wanted to pass on this idea. Mm, next, yeah. So this is an interesting problem. Uh, what is happening over here is body is in a form of solid of revolution. The diameter d in centimeters of its section at distances x centimeter from one end are given below. Estimate the volume of the solid. So we have something like, yeah, let it be. So we have something like, if this is my x. So at 5. So I have this diameters at every value. So 5, 5.5, 6, 6.75, 6.25, 5.5, and then 4. So I have something like uh, this, right? And it is being revolved around this x-axis. So I want to calculate the area of this section, this volume of this solid of revolution, right? So does anyone know how to approach this problem? Anyone? No? Fine. So what we can do is like this is a solid of revolution. So each of these discs we can treat it as a circle, right? So this would be a circle of diameter 5, right? And then this would be a circular disc of diameter 5.5. Similarly, a disc of 6, right? So Mm, we can calculate the radiuses, which will be like half of these, and then we can get the area of this disk pi r square. Similarly, area of this pi r square, and then we simply need to integrate all those areas in this direction, right? So it will be like integration of uh, area as a function of x and then dx, right? And this would be like from 0 to 15 in this case. And each of these areas would be like pi d square by 4. Okay, so you can use any of the method you want, either trapezoidal rule or Simpson's one-third rule or 3/8 rule, anything you want. You can simply calculate these. Like I can make one table over here for a of x, and I can calculate all these areas, and then I simply need to integrate over them. Okay, so basically this would be my f of x, and this would be my x, and then I can use so I will get this table and I can use anything I want, like either Simpson's one-third rule, Simpson's 3/8, or trapezoidal rule. So is this clear to everyone? You guys can speak.
Yes, sir, it is clear.
Fine. So I think I have two more. So yeah, so these are simpler. So you just need to calculate the values of these missing entries. So for the first one, yeah, so since we need to get the value of fx, but we know the value of f dash f prime x at 0.6, so we can use the yeah, backward difference formula for this to get the value of f at 0.6. And then once we get the value of f at 0.6, we can use the forward difference formula for f prime 0.5 to get the yes, we can simply use the forward difference formula to get the value of f prime 0.5. Okay, so this is simple. The next one is you just need to calculate the velocity. So this is similar to the non-graded assignment problem or even the graded assignment problem. Just you need to make sure that the central difference formula gives you a better approximation than forward or backward difference formula. So for all the points in between this table, you need to use the central difference formula because you have the point just afterwards and just before and just afterwards. So the central difference will work for all these middle points. For this end point, you need to use the forward difference formula because you have no point after before this. And similarly, for this end point, you need to use the backward difference formula because you don't have any point after this. Okay. Uh, yeah, so this is also, I hope this is clear. So this is all from my end. If you have any doubts, you can ask. Otherwise, we can end this meeting and we will meet same time next week. Fine, then I will end the meeting. See you guys next week. Bye.
तो अपना बोल